We are going to collide our two worlds of parametric equations and vectors for what we call vector valued functions. Okay. What is happening is instead of having a set of parametric equations, those parametric equations are inside of a vector function. Okay? What does this mean?
I got no clue. Alright, are we in radians or degrees?
I'll let you answer that. What are we in?
It looked, I don't know.
If we're working with a general trig equation, it needs to be radians.
Where's the trig? I don't see any trig.
There is no trig on here, which is why I don't know why.
So is it degrees?
Did you listen? I just said if we're working with a function in general, it needs to be in radian mode.
Wait, you said trig. Okay, so
He was
it's in
asking a
radians.
general question. There's no trig up here. I don't even know if we're doing trig today. I don't know.
So
But if we do trig today, it needs to be in radian mode. Okay?
Okay.
Okay.
There we got it.
Now,
I didn't have a problem.
This is what we worked on last week, a set of parametric functions. We also worked on vectors. Now we're putting that set of parametric equations into our vector. So whatever's in front of our I vector, that's like our X equation. Whatever is in front of our J vector, that represents our Y equation for our parametric set. And what happens when I plug in values for t, we draw a vector to get us to the coordinate. When I plug in 2, we draw a vector, and that gets us to a coordinate. When we plug in 3, it draws a vector and gets us to that coordinate. To where we have this graph still with direction, but it's drawn using vectors. Yes.
It's just kind of like Euler's method.
No. It's basically, instead of the parametric equation giving me the coordinate 1, 2, this gives me a vector 1, 2. Okay? What would the purpose of this be? We're going to use this to help us understand the velocity and acceleration in the two different directions of our movement simultaneously.
Wait, so are you like those vectors, are you just filling in like in between them, or just an infinite amount of like vectors?
We have an infinite amount of vectors that are drawing this curve. So instead of getting the coordinates that we string together, the vectors are drawing there, and we're getting the same thing. Okay. Okay. In radian mode, turn your brains to radian mode. Okay. If this were our set of parametric equations, this is how we would write it as a vector valued function. Why there's so much space. Okay. We are going to draw the graph of this once we get it written down. Was there a black pen in here? Is that what you like it? I don't want a black pen. Anybody want a free pen? It's actually black. With a red cap.
Cool. That's just not confusing at all.
Okay, were you not participating in the final Friday tonight?
Oh, I leave after this hour, so.
So you didn't work.
Yeah.
That happened again.
The answer is just no.
Huh?
Nick, did you finally buy one?
Yeah.
I participated the first week, yeah.
Okay.
Well, I don't know.
I have like 8 of them.
Alright, can we do that this
All right.
Not word, or, math is-
I don't own a flannel. What is a
I
flannel?
didn't either.
Okay. If I plug 0 into our vector valued function in radian mode, what is the cosine of 0?
Why? Zero. Matthew, what's that shirt you wear?
So we have 1i plus, what's the sine of 0?
Zero.
Okay, so we have the vector I. So the vector I looks like this, and we have a coordinate for our curve. Okay. What is the vector we get when we plug in pi over 2 to our vector valued function? Benjamin, what would we get? What's the cosine of pi over 2?
Is it zero?
It is 0. What's the sine of pi over 2?
Is it one?
So we have 0i plus 1j. So we have the vector j. Okay. What about when we plug in pi? Richard, what's our vector? Okay, negative I. So we have our vector negative I.
Whoa,
It's a circle. You knew that to be specific.
Okay, and when we plug in 3 pi over 2, Marina, what would we get? Negative j. So our vectors give us this circle that is going counterclockwise. Are you understanding how we're colliding these two worlds?
Gotta say yes.
Are we gonna have a quiz on this before we finish the break?
No, we're gonna, so this lesson is going to get paused, and you'll have some homework. We'll unpause on Monday, and then Tuesday we'll talk about like velocity and acceleration and all that stuff. Okay. Your turn. Nope, just kidding. I lied. Well, maybe I will say your turn. Go ahead and write this down. And I want you to discuss at your table what you think the domain of this vector valued function would be, and in general, what we would have to consider when we were looking at the domain of a vector valued function.
I feel like you're the only one
Well, we.
Well, I mean, that's the I component. The I component has to be restricted to
With the t squared,
zero.
positive t, j values. For,
about to disappoint.
yeah.
Domain is the x.
Alright,
So
cool.
Yeah.
my final answer is between -1 and 0, that's the domain.
Well, I
Is
mean,
the t
it could
squared,
be
right?
between negative 1 and 1.
They want to positive.
So
It's gonna be
negative
weird
one,
here.
two, one, with brackets because it's inclusive. So when the range goes negative infinity to
Wait. No,
just
it's
ask
only
for
zero.
Or you want-
the y component can go
That's
squared.
true.
You are
It
right.
surprises me that
Inclusive of
that's
all.
something that you would know.
It goes like.
No, inclusive. No, you are correct. I misspoke.
Because that's fine.
I don't think I should read it.
Okay. The domain. Caleb, what's our domain?
The big boy, but I don't know what this means.
Oh, it's gonna be.
I feel like it could
it's
be
like
anything.
more compressed.
That's the big
Okay. Caleb is saying our domain is all real numbers.
I disagree
Why?
because I think it's from -1 to 1.
So you're thinking of the range of sign.
Yeah, you're thinking of
the
the
wrong
range. Oh no.
Isn't the I the x?
Yeah.
Well, okay. So sine would have a domain of all real numbers.
Yeah, but
And t squared has a domain of all real numbers. Therefore, overlap the two, we have a domain of all real numbers. Okay? Now, Nick, what would happen if I change this to be t to the 1/2? Now what is our domain?
0 to infinity.
Okay. Now we have this has a domain of all real numbers, but radical t has a domain of 0 to infinity. So as a vector value function, the domain is the overlap between the two, 0 to infinity. If I can't plug it into y, I can't plug it into the x. Now, when you think about domain, I want you to think about the domain as this as a function separately. Like if we had just y equals the sine of x. And then I want you to think about this separately, y equals radical x. What would the domains of those be separately? Now where's the overlap? That's the domain of our vector valued function. Does that make sense?
yeah.
Okay. You were thinking like this belongs to x and this belongs to y.
Yeah.
Okay, so we're just going to think of them separately and then
Okay.
overlap them. Okay? All right.
Domain is just a number.
Same
Plug
thing.
in.
Plug it in, right?
No, I want the graph.
In radians.
This graph is
Now,
the next value.
let's think back to our parametric day when we did our parametric graphs. Do we have to always plug in values? No. So let's think about this. If this is our vector valued function, we can still think about x being 2 cosine t, and we can still think about y being the sine of t. And what would make our lives easier in terms of figuring out what this graph looks like without having to plug in values?
That's an eliminate.
Okay, it's an ellipse. How do you know that?
That's what we
Trig.
know.
Because we're adding
It's in radians.
How do I? What trick do I need to use to write it in the ellipse
Sine
mode?
squared plus
Pythagorean
cosine
integral.
squared
Equals what?
equals 1.
Okay. So the cosine of t is the same thing as x over 2, and the sine of t is the same thing as, oh, I guess just y. So we have x squared over 4 plus y squared equals 1. So when we go to make this vector valued function graph, don't try to say it too fast. We have an ellipse with a center at, okay. Since 4 is under our x squared, we're going to go out radical 4 horizontally. Since 1 is the denominator for y squared, we're going to use square root of 1 for our vertical distance from the center.
Yeah. That's what I learned.
Okay. Is this a clockwise ellipse or a counterclockwise ellipse?
I would say counterclockwise.
Matt, how do you know it's counterclockwise?
Because trig functions go counterclockwise.
That's not it.
But the last
But it's
example we did, it was counterclockwise. It was basically the same.
Those are both positive.
Because they're both positive
Because you
and
plug
both
in
going
numbers.
counterclockwise.
Now, that's not a bad way to look at it.
Isn't that
Okay.
like you plug
Since
in-
they are both positive, we do get the effect of when we plug in 0, then when we plug in pi over 2, we are going to go counterclockwise. Okay, but I would not just guess. Use some logic, whether you plug in numbers or not. Okay. So I printed off my notes from, I don't know, this might have been last year or 2 years ago, I'm not sure. And this is what it says on this slide.
No, thank you.
No idea why, but I'll just leave that there for you.
I like that.
Because we're doing excellent. E to the excellent.
Yes. Okay. We can take the limits of vector valued functions. just like we can with normal functions, okay? If I ask you to calculate the limit of a vector valued function, then you basically take the limit of the horizontal component separately from taking the limit of the vertical component. It's not very exciting. I bet you could have figured that out without me telling you, but I'll let you know.
No, are we looking at it like that?
We're just playing like because technically like the
So
exercise
what's
goes
day going?
It sure is going.
That's good. Better than not going.
Plug
I
in
know.
theta sign? Or ampersand?
You gonna grow your hair back out, Chris?
Yeah, you could plug
Yes,
in
sir.
any t value. So we talk
Yeah,
about
that's the
domain.
Right up until I cut it.
Domain of T, not domain of X. I misread.
You are thinking X.
domain of X, yeah.
Yeah. So when I talk about the domain of a parametric or vector value function, we're thinking of t because our inputs are t, and that's how we define domain.
Is it like a once a year haircut kind of deal?
Yeah. Once a year. It's usually once a year though.
I have a vector valued function that I would like you to evaluate the limit as x, not x, as t approaches 0.
But it's
Just so you know, it's not a plus sign.
I don't know. I'm using this today. Right up until the wait a second.
I know that from somewhere. Flashback to Calc. No, if I choose not to, I don't know the steps.
I think
The
it's
zero.
RHA.
And now I actually
Wait,
know
you don't
why.
even take the derivative?
I know why it does that now.
No, it's one.
You don't even take the derivative of them, it's just like, oh wait, no, never mind.
Either that or the identity. Yes.
It's just the limit of each individual one, right? Each individual, just plugging in 0, right? But the other one.
Did we learn about that? Right here. First page.
Over 0. No.
Anthony. What's the limit as t approaches 0 of e to the t?
Anthony's Bernoulli's.
Yeah.
Well, no, I asked you for 1, and so 1i. Okay. Now, when we take the limit as t approaches 0 of sine of t over t, we did have a rule that if you have the limit as t approaches 0 of sine of t over t, it equals 1. Some of you are using L'Hopital's rule. That's fine, but it is a rule that you learned in like your first week of calculus class.
Yep. Chapter 1.3, special limits.
Yep.
This is my Calc one notebook. Not anymore, no. You're disappointed.
It's probably in August, though.
Whoa.
I guarantee you it was in August.
Yeah.
Okay. Continuity. Right after limits came continuity.
Oh, my.
I guess that's true.
This is a good review.
What do we have here on continuity? Oh, yeah. Homework.
Don't go back and look. I want us to remember off the top of our heads. Okay. We have 3 stipulations for a normal function being continuous. We are just going to adjust them for our vector valued function. Okay? Zane, what is one thing that has to be true in order for our function to be continuous?
the limit for both sides have to go to the same number.
Okay, so the limit has to exist. So we're going to say the limit as t approaches a of r of t exists. I'm always afraid of
Why are we
misspelling
using
it
A now instead of C?
because we're doing vector valued functions. So I really want to make sure we can differentiate, pun intended, between the two.
Between one variable and the other one? Doesn't
No, like like normal
Wait, so-
equations and vector value functions. They're different worlds. Okay.
So we're still using R of D.
Yes. And technically, I should probably have R bolded because it's a vector valued function, and so you will see that that bolded letter for that. Okay. Okay. For continuity, Haley, what's something else that has to happen? We have a limit that exists. Not for continuity, because we didn't learn derivatives until well after continuity. So if we have a limit, what else do we need? Yes. Okay, so R of A, that's an R. And then what has to be true?
They gotta be the same.
They have to be the same. Okay, the limit has to equal.
One thing that is bothering me, at the start of this, you said P of T equals F of Ti plus G of Tj, and now you're using R's and T's.
Oh, we can name them anything we want.
I know, I'm using P, but it's just kind of bothering me that you started with like
Sorry.
P and now you're working with R.
Okay, at your pod, discuss where this vector valued function would be considered continuous. Wow, the discussion is just overwhelming right now.
I'm writing.
Writing it down.
Fair enough.
So she'll learn that.
Well, it has a domain from one to,
There you
but it exists
Stop with your
when t
card.
is greater
What are your
than
thoughts?
or equal to. So it exists, yeah, it exists on the range of 1 to but is it necessarily?
go.
I think it's
The domain
goes down to
And then it
hops, skips, or jumps.
where the domain is, there's no point to just continuity.
We've seen it before.
Group graph.
radical graph. Well, we've seen like radical graphs before, square graphs before. Really
Yeah.
like this.
Yeah.
That's my.
All right, Isabel, where is this vector valued function continuous? Not including one?
Not
Including.
I would say including
Including.
I'm disagreeing.
Not including.
Including it.
Richard, you seem to be the only one saying not including one.
Okay.
Why wouldn't you include one?
A 0. You do that.
Try it in your calculator. Radical 0.
Hey, are you in
You're
radian
gonna give me 0?
Agree. Agree might be 0.
Zero
What
times
squared
zero is
equals 0? Say 0 squared.
But 0 to infinity you
I thought we were over this, Richard.
Okay, I'm gonna give you guys a break. So drop your pencils. Okay.
So that's just clowning you, right?
So this is the definition of a derivative. Do you agree?
Definition, yes.
Okay. So if we define that R of t is function fi plus function g j,
Sounds like you're dumb.
Okay. Let's go ahead and apply that to the limit definition of the derivative. Okay? So we have the limit as h approaches 0. R of t plus h would be f of t plus h, I plus g of t plus h, j. Minus r of t would be f of t, I plus g of t, j, all over h. Okay? Well, do you see how we can maybe like group these fractions together differently?
Yeah.
Could I group f of t plus h minus f I plus f of t I together plus, and then I could group g of t plus h j minus g of t j together all over h. So I could take this and say, well, this just means f prime of t, I. And I could take this with the limit and say, well, this is just g prime of t, j. So if I want the derivative of a vector value function, we can just take then the derivative of f times I plus the derivative of g. You okay with that?
So it's just the
Yeah.
derivative.
Yeah, you gotta put in circles too.
But don't include the stuff in red.
So R.
That was applied.
Then you just have two green circles there. What if someone had-
Exactly, that's the, Benjamin?
When two people strike you, they have this. I heard they say this. Fight me, Chris.
Really?
Alright, next slide.
Stop. Write this down. If you were to make a guess as to what this vector value function looked like on a graph, what would you guess?
Let's go with some type of curve.
If x equals t and y equals 4 minus t squared, how could we eliminate the parameter?
Oh.
Y equals 4 minus x squared,
Upside
right?
down. Yeah. And it's also minus 2, 4. Shifted up.
And reflected.
Yeah. Remember this from going outside or pre-calc?
It's also a
This.
direct. Yeah.
Function aerobics. Okay, so that's what we're working with. Now, R, that's not an R. I definitely drew an F. R prime of t would be, what's the derivative of t? 1. Plus, the derivative of 4 minus t squared would be
2t negative 2t.
So that would be R prime. 1i plus negative 2tj.
Wait, so.
So what? Okay. Richard, R prime of 1, what would it be?
What?
If I plug in 1.
What?
If I plug in 1 for t,
Yeah.
what vector do we have?
Oh. I minus TJ.
Okay. Now, at r equals 1, that's a 1. We would have the vector I plus 3j, right? which is right here. Okay? If I plot r prime of 1, where we're on the graph at t equals 1, we're going to go right 1 down 2. I would have that vector right there. Looks tangent, right? Okay. Some of you physics people like to think of the normal vector, right? Okay, that would be the normal vector.
So why can't you just do negative 2x for the derivative instead? Because you got y equals 4 minus x squared.
We're talking about a vector valued function. So we need to keep it in vector form when we take our derivatives. Now, we can do this to help us with the graph, just like we did in parametrics, but we still have to stick to our vector valued function form.
Okay.
Okay? Our normal vector would be what? This one in particular. 2, 1?
How'd you know that?
Because it needs to be perpendicular to the tangent vector, and if our tangent vector is 1, negative 2, then opposite reciprocal for slope, the vector would become 2, 1.
Why do you choose negative 1 then?
No, because our slopes need to be opposite reciprocal. And so this slope
Oh, it's negative altogether.
is negative. Okay, so you have a homework assignment. I don't even know if you'll have to take derivatives in your assignment or not. I really can't remember. We will pick up here on Monday, and we will talk about the curve being smooth, and then we'll talk about antiderivatives and the fundamental theorem of calculus. Okay? That's where we're going with all this. To be honest, the math that you are doing shouldn't really feel new. It's all old concepts. We're just in a different form. You know what I mean? Okay. Enjoy your weekend.
Thanks. Thank you.
Well, like you guys are like sitting there. Like, are you gonna go?